Hello. Let's discuss a little bit about electromagnetic waves in vacuum. We, you know that electromagnetic waves come from a fundamental consideration of Maxwell's equations. So when we look at Maxwell equations in vacuum, they tell us how electric field and magnetic field, what kinds of laws they should obey. So we're looking at a point in space, and maybe the electric field is that way, maybe magnetic field is that way. So we're gonna so this is x, y, z, and it will vary at this point in time, and we want to find the laws that they obey when this happens. So one of the laws is this, and you might say this comes from actually Coulomb's law, and there is a charge density on this side, but because at this point there is no rho is 0 here and J is 0 here. So rho is the charge density. So there are no charges at that point, and there's no current flowing through at that point. So this is called current density. So at that point, this will be one of the laws, right? Another one is del dot B equal to 0. That's always true. And then you have a del cross E equals to minus dB dt. This also true, minus here. And del cross B is mu naught epsilon naught dE dt. It's kind of cousin of that, but it's got this factor. There it is 1, okay? Minus 1, so to say. So, so this came from Coulomb. This has a known name. It just means no magnetic monopoles. And this is the famous Faraday Law. And this is Ampere's law. But this term is a term that is not in Ampere's law, and it's called Maxwell current. So it is coming from Maxwell. This stuff has units of current density, and you might call it Maxwell current density. There is a term here, mu naught J, for the real current, and because current density is 0, this term is missing in vacuum. Okay. So electric field are supposed to obey these 4 laws, and we can show that from these 4 laws, you can show that del cross E, del square E is equal to you can say mu naught epsilon naught d square E dt square. This del square stands for del dot del, and you might remember del, I didn't explain there, del stands for, say, dx j hat dy plus k hat dz in Cartesian. It will have different forms in different coordinate system. For instance, it will look a little different in a spherical coordinate system or cylindrical coordinate system, but I'm not going to go into that. We will work with just Cartesian in this course. So one thing, this, so electric field if you can simplify it, that one of the consequences of those is this. Another consequence is del square B is mu naught epsilon naught d square B dt square. So if we find solution of these guys, and those solutions, the sub-solutions, okay, for which these guys are also true, then that will be solutions of Maxwell's equations. So here is the upshot. So let's call it A, B, C, D. So those four equations. So the strategy is this. So you have a solutions of 1 and 2. And then here is a subset that also obey A, B, C, and D. So that's what we want. So these will be the solutions of Maxwell's equation. Like wave-like solutions of Maxwell's equation. So solutions 1, 1, and 2. Let's look at what we want. So what will this be? Solutions 1 and 2. Because this is because 1 and 2 are wave, so these are classical wave equations. So there are 3 of them here, 1 for each component, 3 of them. So it's like a d del square Ex equals mu naught epsilon naught dt square Ex. So I can use this shorthand notation like over here. This dx stands for ddx. Similarly, dt stands for ddt. So dt square is a second derivative. And del square Ey equals to mu naught epsilon naught dt square Ey. Del square Ez equals to mu naught epsilon naught dt square Ez, right? And similarly for this, similarly 3 equations, 3 equations for this. Okay, now when we want to study still on 1 and 2, we still solution we're looking for, type of solutions. So kind of solution we want, we can say what kind of solution for this I want. Just look at 1 and then we'll see similar. So we have a choice between standing wave or traveling wave. So this will be the case if my system is finite dimensional. And this will be the case when it is unbounded, right? Dimension. So we are actually going to do this today, traveling wave. So we're going to look at So we're going to have a traveling wave. So what does it look like? It look like Ex of at x, y, z, t. That's what we want. We want a answer to that question. What kind of function of x, y, z, x component is? So this is very easy to confuse. This just a label of component. I could call it 1, and these are the you might say coordinates of the field point. This is the field point in space. So don't confuse this x with that x. The only thing is this x must correspond to some x coordinate, and this is a component in that direction. So there's a relation, but this will have some real values, but this will not have real values, right? This is just a label. Okay, so this will look like E0x cosine kxx plus kyy plus kzz minus omega t. If it's we're just going to write like this, plus phi x. So this is a wave. So there are 3 waves here. There are 3 waves here. So this is one of the wave. So if I want to write all 3 waves, sometimes we write as a complex notation. We might say E0x e to the power r k dot r minus omega t plus phi x. We can write, and we're just looking at the real part of that, right? We can write in that notation. When we write that in that notation, you can see that k is a kx I hat plus ky j hat plus kz k hat, and the r is just x I hat plus yj hat plus gk hat. You can see there is a little problem here. I'm using this k for the wave number, and this k is nothing to do with this. So there are 2 uses of symbol k. And so you say, how do I write down the unit vector in the direction of k? Well, that's going to be a problem because I'm going to have the same notation. So k hat may mean k hat is not necessarily along the, you say, okay, I'm going to just k hat for this notation, then you're going to run into trouble. So often when people write this, instead of using I hat, j hat, k hat, they end up using k as a kx u hat x plus ky u hat y plus kg u hat z. So this is just I hat, this j hat, this k hat. This is too much writing, right? Another notation that's common use is kx x hat plus ky y hat plus kg g hat. And I kind of prefer this because I don't want to write too much. U is just like reminding me it's a unit vector. So there are like 2 things reminding. This reminding me of the unit vector, this reminding me unit vector. There are 2 different things reminding me unit vector, the same symbol. It's just a redundant. So I like this, okay? All right, so we can write EY similarly. E0y e to the power I k dot r minus omega t plus phi y. Ez xyz t I can write the same way. Okay, so this looks like this will obey the equation 1. So equation 1 seems like I have a solution. Will mean that if I plug in there, I will have a kx square plus ky square plus kz square equals to mu naught epsilon naught omega square. Often we also write mu naught epsilon naught equals to 1 over c square. So it's just whatever the speed, you can see that this is the speed of this wave. So I can actually use this, because I'm talking about light, in anticipation of what it will be, I'll just use the letter c. So you can say I got k square equals to 1 over c square omega square, which will mean omega over k is c, or omega equals to k times c. So as long as this is the relationship, I have the solution. And there will be similar solution for the b, for those 3 equations of b, but we don't need to work them out separately. Okay, so I've got these. How about, do these satisfy? And I need to restrict them in here. Do satisfy a, b, and c? So let's look at what it will take to satisfy a, b, and c. So plug into a. Does it satisfy a? So I take these solutions over this solution and plug into that. So that is actually dx ex plus dy ey plus dz ez equal to 0. So it says that dx ex, so take a x derivative of this, kx will come out and minus sign, minus kx, and cosine becomes sine, e0x sine kxx plus kyy plus kzz minus omega t plus phi x minus ky, and similar thing for, and in kz similar thing but not same, that equal to 0. Let's take an example. This is complicated, so we'll see. Take an example. Say the wave was traveling in the z direction. So I want a traveling wave along z direction. Towards positive z axis. Well, these solutions, you can say that these guys are not there. That means kx is 0, ky is 0, and we'll just set the same thing in all of these guys. So that will mean kx is 0, ky is 0, and so kz will be the whole k. It's going towards that, so it's going to be a positive component. So what does a look like for that? So this will mean a looks like, when I take an x derivative with respect to, there's no x here, then I'll have 0. So I'll get a 0. When do the y derivative of this guy, there's no y there, then I get a 0. And then when I take a z derivative, I get minus kz e0z sine kz z minus omega t plus phi z equal to 0. Now this is supposed to be true for all x and t. Okay, well, think about it. Well, this is this stuff maybe 0 someplace. Sign will have to go to 0 and between 1 and -1, but it's not going to be 0 at all places. So rule that out. This is not 0 at all places. And all t, okay? So it has to be the product of this to be 0. So I have a k, let's call this guy k. K times E0z has to be 0. Well, if k was 0, let's see what will k will 0 mean. If k was 0, I don't have traveling wave. I just have oscillation. If k is 0. So I don't have a wave. So k, since k cannot be 0 in this example, that means E0z is 0. It's a very powerful answer. So what is saying that if an electromagnetic wave in vacuum is going towards the z-axis, electric field at any point can only be in the xy. It can only have x and y component. So at this electric field here, which is equal to x hat ex plus y hat ey plus z hat ez, this is not there, okay? So electric field can only have x component or y component. So like E x, y, z, t, if you look at the wave, it's going to made up only 2 waves, not 3 waves. E0x cosine kzz minus omega t plus phi x plus y hat E0y cosine kzz minus omega t plus phi y. It's going to be just like this. The third part would have been z hat E0z cosine kzz minus omega t plus phi z. Because this is 0, that part is not there. And because there's only one k here, we can just write down k here. If you want, you can just write down little k for that. So I need to just, instead of 3 electric waves, I need to only work out 2 electric waves. All right, let's study the same example. Now that we found the electric fields, so we had the whole solution of 1 and 2, and then we looked in here. Here it seems like for solution of traveling wave towards positive z-axis, electric field is only x hat ex, not vector notation, y hat ey. That's pretty cool, right? How about the magnetic field? Do I need to work out magnetic field separately? The answer is really will surprise you that you really don't. Now, if you know the electric field x and y component, there is a we can try to see what either of these 2 laws, what this like Faraday law says, or so let's look at what the Faraday law says. So if B is, you can have a Bx x hat plus By y hat plus Bz z hat. So if I had dtB, there's no derivative of those guys, time derivative. So you have a dx bx, a dt bx plus dt by. This is x hat, y hat, dt bz. And you have a del cross of E on the other side, and the minus of that will be minus these guys, right? Minus, minus. So del cross E, well, how do I get? We have to do x hat, y hat, z hat, dx, dy, dz, ex, ey, 0, because there's no z component. So if I go over here, I only get that. So get x hat minus x hat dz ey, and then I have, if I go over here, I get this minus, so minus y hat dz ex. Is that correct? If I do it this minus y hat and this minus, so this will be plus, and when you go to z hat, I go this, but this derivative is x, and these guys, our electric field don't depend on x in our example, so this is 0. So I'm going to see what this says in our equating this. You can see that I have a x hat dtb. So just equating x hat with x hat is dtb sub x is equal to dz by, ey, and dt by equals minus dz ex, and dt bz equal to 0. So you can see that you can show that this would mean bz is 0, okay? Like b0z is 0. So we find that if my electric field waves were going along the z direction, we proved that electric field can only have x and y components. We also see that magnetic field can also have only x and y components. So both electric field and magnetic field are transverse. Both E and B to direction of the wave. This is the direction of the wave. So that's one notice. And when I look at these guys, I say, okay, when I take a dt, I'm going to get what? I'm going to get a omega b0x. And on the other side, I'm going to get a kz omega will come with a minus, and this kz will come with a plus for a wave going that direction, E0y. So I really don't need to know this can be obtained from E0y. And the other one is going to have minus omega B0y will come from taking a derivative of that, and minus kz E0x. So you can see that if I knew E0x, I can get B0y. And if I know E0y, I can get B0x. So independent components here are, I can, independent pairs, I have a choice. I can choose these as a pair, these as a pair, I can choose these guys as a pair, I can choose these guys as a pair. So I can take one from here and one from here. So independent pairs are B0X, B0Y. You can choose that and you can get all the E's. Or you can choose E0X and E0Y and you can get the B's from there. Or you can choose B0X, then you have to choose E0X. Or you can choose B0Y, but then you have to choose one from the other guy, and there'll be E0Y. So there are 4 different ways you can do it, and you know, we can just say, well, we want to just work with this pair. That's the convention. You work with this pair and you can get the B's from there. And you can see how you can get the B's. The relationship that exists here, omega over k, if I bring over this side, so minus omega over k B0x E0y, and this is same as equal to C. This one is going to be omega over k, kz becomes k, because it's going along the z direction, B0y equal to E0x, and this is C. See, if I choose them as an independent pair, then I can get these guys by dividing by C. In one case I have to put a minus sign, in the other case I don't put a minus sign. All right, let me see how I did. Okay, so let's recap. Traveling wave. Now moving towards positive z axis, and let's choose EX and EY waves to be independent pair. So what we'll have is we'll have EX equals to E0X cosine kz minus omega t. Let's also pick t and z t equal to 0 and z equal to 0, so that phi x equal to 0 and phi y equal to 0. So we can choose these 2 choices, make those 2 choices to set 2 constants to 0. Of course, if we have more waves, I won't be able to set them, but at least I can set them to 0 here. Cosine kz minus omega t. So they're same. So those are the solutions, and clearly Ez equal to 0 in this solution. Okay. So that's electric field. So electric field is if I look at z equal to 0, t equal to 0 in the xy, it's got E0x and E0y. If you set all this, it's going to be like that. So it's going to be that vector will be that way. And if I wait at z equal to 0, I wait, you can see that this is going to move back and forth. So this is an example of what is called plane polarized EM wave. Okay, we'll have more to say about polarization in a minute, but right now we need to say other waves that Other waves that are associated with Vm is magnetic part, right? Other waves will be the Bx, By, and Bz waves. And what do they look like? Once I know those things, I know By equals to 1 over C Ex, and Bx equal to minus 1 over C Ey. We just showed that. And Bz equal to 0. So these two mean transverse wave. Why do I mean transverse? It's going towards the z-axis, and z component is 0, right? So the only x and y comes. So the electric field and magnetic fields are like here. Okay, so that's the solution that satisfies. That's the solution for something on the z-axis that satisfies the Maxwell's equation, and it's based on the wave equation that's hidden inside the Maxwell equation for vacuum. Okay, so we can write. Actually, can write. It will be nice to write this as a vector form. So I have E is like this, so I could write E0, like I can write this guy, this vector is E0 vector. So E0 can be x hat E0x plus y hat E0y, right? And then I could write B0 as x hat. These are B0s, B0, okay. B0 B0 B0x plus y hat B0y, and so electric field wave is just E0 cosine k dot r minus omega t, and B is 1 over C, maybe just want to call it B0 because it's a B0 cosine k dot r minus omega t. And B0 is actually 1 over omega k cross E0, and I haven't shown this how. Well, if B, you write B0 e to the power I k B0 vector k dot r minus omega t. Suppose you write like this, it's much easier to see. dt of B vector will simply be minus I omega B. dt of B vector will be this. So minus dt will be plus I, and del of E will be so I write E as a exponential, so it will be easier to work with. So if I take a del cross of that, so del, when it hits the R, it brings the I k. Cross leaves this exponential leaves it alone. So unlike working with cosine sines, where your cosine goes into sine, you just get the same thing back. So when you equate them, you get a omega B equal k cross E. So you can see that you can write B as k over omega cross E, and you this is the one of the speed light, and this is the direction. Say k hat direction is represented like this, or you can represent like maybe u hat k vector direction. So if you say you use this overkill, but let's use that. That will be magnitude k omega u hat k direction. So unit vector along the k hat directions, and this is just 1 over c u hat cross e. And cross is why you get a minus here and a plus there, because the cross. One of the things about this thing here, look at closely, you have a b cross e. Now I wrote in vector form, and I didn't really work out the very nasty calculation here, but from the z you can see how it will work out. So if the k was along the z direction, say it's the z hat direction, and this is x hat direction, then this will be in the y hat direction. You can see this relationship of the cross product. So if this is a propagation direction, then I go from e vector to b vector, and this is the source of right hand rule. Okay. And another way to look at it, if this is the relationship, so if in the cross product, x hat cross y hat equals to z hat, right? And y hat cross z hat is equal to x hat. So if I'm writing x hat cross y hat, so I could actually, just looking at the direction, I could have a direction wise the direction of the electric field, so let's call E hat, cross direction of the magnetic field will be direction of the k direction, the direction of the vector. So these are unit vectors along the electric field and unit vector along the magnetic field. So you could see that E cross B vector is in the direction of wave or wave flow. Okay, so energy actually, when you work out energy, I'm going to work out energy next. When we work energy, we are going to see that this kind of cross product plays a very interesting role. Okay, and there is a quantity that we define to write all of these things in, a quantity. Let me, because there's a space over there, we will introduce what is called pointing vector. Okay, and that will be written as S equals to 1 over mu naught E cross B. And this mu naught is for some reason that will be important later. Okay, so next one I'm going to talk about is the how to study flow of energy in this wave. All right. Okay, let's get into a little bit more interesting thing, such as intensity of light, or in general, intensity of EM wave. So we studied a plane polarized EM wave. So what we had was a EX wave and a EY wave. So these were our pair, so-called independent pair, and and we also had a EZ equal to 0 for wave traveling towards plus z axis. And from these we're able to get Faraday Law. for instance. When we use Faraday Law, we got the Bax and By, and Bz turned out to be 0. So we choose this, and we got the answer for this. So just it's a recap of some things that went on before. This was Ey over C, and this is Ex over C, and this we choose some amplitude, and this is Kz minus omega t, because plus z-axis, and E0y cosine Kz minus omega t. Okay. We want to know, this is a wave traveling through some space, and say if I put a screen and our area, put an area in front of it, at what rate energy will flow through this area. So what I want is per unit area. So this arbitrary amount of area, so I want to get per unit area. So this area A. So I want power, because I want per unit area. So power flow, right? I want to know power flow. So that how do I what do I do to get the power flow? You can define as we'll call it S, which is also called power flux. So I want per unit area, so that makes it a flux per unit area. S is how much energy passes through A, some area, arbitrary area A, but I want per unit time. So in time delta t. So I want per unit time, and I want per unit area. Okay. Now this, because these guys are time dependent, so this will be a function of time. So this screen, say this screen is located, if you look at the z-axis, so it's located at z equal to some 0 or something, okay? So the screen located at z equal to 0, or some arbitrary z equal to z0. So wave will have some electric field and magnetic field values here, and I need to add up the energies at different points, right? So that will give me the energy through this. Okay, so what's the energy? Energy in a wave will come from, the energy part will come from energy in the magnetic field, electric field, energy in the electric field, plus energy in the magnetic field. You know the wave is moving with speed c. And for simplicity, we're going to just say this area is in the xy plane, and wave is moving towards the z-axis. So this is the k direction. So this is a simplicity, simple situation we're going to use, but we want to add up like that. So I need to figure out how to, if you give me energy field, I need to know how to get the energy in the energy field. Maybe you have, you remember from studies before, but I will write this formula is we don't have energy in energy field, but we define energy density, energy per unit volume. In energy field, in electric field. So usually written U sub E is equal to half epsilon 0 electric field dot product. So this is a general answer that you will learn in electricity and magnetism course. So if I multiply this by a volume, I'll get the energy in the electric field. So if I'm thinking about some volume and the electric field is everywhere, electric field vectors, they're different place, right? So at each point I will go and do this. So dx, dy, dz, this is the volume element over this volume. That will give me how much energy is contained in energy. So this will be energy in the E, or you can say capital U. There will be capital U. So amount of energy contained in the electric field. It's kind of like a potential energy. Energy. What is the formula for this? There is not formula for that, but again you have energy density in energy density, energy per unit volume. So energy per unit volume in B field, magnetic field, and also very similar formula, but instead of epsilon naught, it is mu naught in the denominator, to mu naught B dot B. And again, if I want in a volume, I will have to integrate over a volume UB 1 over 2 mu naught UB dx dy dz. Okay. Now, if you go by electric field and magnetic field, they are time dependent, right? So these guys will be time dependent, and that will make this guy time dependent. That's where the time dependence comes from. Okay. Let's see. If you give me a solution like this, electromagnetic wave like that, how much energy can I expect? Okay. So I am going to even simplify to further. I will say simplify further. So I will take EY equal to 0. That will mean BX 0. So I'll take EX equals E0 cosine kz minus omega t, and EY equal to 0. So I'm taking if this is Z and this is the x-axis and this is the y-axis, so I'm taking electric field pointed that way at some point. So if you take a Z equal to 0 here, and if you look at t equal to 0, electric field point is that way. Of course, electric field at different times is going to point back and forth, right? Sometimes it's going to point this way. Maybe it's a bigger electric field at that point. It's just an oscillation at this point. So that's the case. In terms of magnetic field, I got a Bx it will be 0, and the By will be whatever this Ex is, E0 over C cosine kz minus omega t. Well, so how much is this UE? Okay, UE, which is a function of z and t now, it's going to be half epsilon naught dot product of this itself. That's going to be E0 square cosine square kz minus omega t. How much it will be ub? I'm going to write this as a b0 y, just for here. 1 over 2 mu naught b0, which will be same as b0, b0 square dot product cosine square kz minus omega t. All right. So at any point, this is point z, some point z is equal to 0 will be here, some point z and some time t. When I add these guys, I will get a in energy in both of them will be plus b, and you can see that if I were to take these guys common, these are equal to each other. You can see the half epsilon took a common and have a E0 square plus 1 mu naught epsilon naught B0 square cosine square kz minus omega t. So far so good, right? If you look at this thing, this is nothing but E0 square, because if you this guy is c square and E0 over c square, so c square will cancel out, and so I get 2 times E0 square, and that 2 will cancel this guy, so I get a epsilon 0 E0 square cosine square kz minus omega t. So I got total energy I can find, but I want to know how much will pass through it in time delta t. So let me get another piece of paper. So we want to find how much will pass through it. So here is a z-axis. I'm over here. I'm looking through this area, how much will pass through it. Well, pass through it. Guess what? It's going with at speed c, right? So all the energy that's over here, c delta t, so in this volume, whatever the energy is in this volume, is going to pass through here. Well, we have this is the formula for energy. So we have this times c times delta t that should pass through it. So I need to figure out, it doesn't depend on this x and y, right? And so if I just freeze time, if say t equal to 0, then I will if z equals 0, then this one is z equals to, if this z equal to z0, then the z0 minus c delta t. So you can see that I will have something this times the volume c delta t, and a times c delta t. So you have energy times c. That's what st will become. So st, so s of t will just become u of the total energy, which is a function of time, times c. It's not very these frequencies that we're talking about are very large. Okay, these omegas are very large. So if you look at omega over 2 pi for these values, they're like 10 to the power 14 hertz for visible light. They're very large. Of course, for radio waves, it's 10 to the power like a megahertz, maybe 10 to the power 7 or something hertz, 10 megahertz or 100. So the 100 megahertz. So, you have, these guys are very fast fluctuating signals, and what do you want is a time average, and that is what's called intensity. So intensity defined by time average. So I'm just going to set z equal to 0 just to make it calculation come out simple, but it's going to be same even if z not equal to 0. So we write like this: s, sometimes don't say what's I'm averaging over, sometimes you say time, you just average over time, or sometimes you can write down whole thing. So when you have a function f of t, how do you time average it? Well, if this is periodic, if it has some kind of period, then it's very answer is very simple. You just have 1 over period, and then maybe 0 to period, f of t dt. So that's what I will say, f of t time average. Okay, but it's not periodic, no period, then time average means time average between t1 to t2. This is a separate kind of time average. I have to tell you, you're not going to get one unique number, right? You're going to get depending on which range of time I'm supposed to average over. So t2 minus t1, t1 to t2, ft dt. So that's the meaning of time average. But our signal is u of this guy is periodic. So for us, this looks like, in my example, epsilon naught e naught t square cosine square omega t. So at z equal to 0. Okay. So when a time average this guy, I'm going to get epsilon naught e naught t square and time average of cosine square omega t. Now this is a periodic signal, and cosine square, if your time average is 1 period, it's going to be half. You can do double angle and then show it. So this back to half is 0 e naught t square, but there's no time anymore. So this is, you can say this is the formula for the intensity of light. But I think I missed something. Maybe I missed the factor of c. So I missed that guy. So I was thinking about some. Yeah. So that's, so c times epsilon naught e naught square. Thing to notice here is intensity, which will usually symbol I. So the thing to notice here is intensity actually goes as e naught t square. This is a big message, okay? Of course, the factor that multiplies to get to the intensity is also important. It's very important when you're looking at like a reflection of light of a surface and how much can get refracted, because the medium will change across, right, when you're reflecting and refracting light. So it's important in a lot of places, but we say that the amplitude square is what gives you intensity. So this is like a often spoken rule, amplitude squared. Okay. So if I were to write in magnetic field, so I wrote electric fields. If I were to write magnetic field, what do you think is going to be the expression? Well, this will have to be c square c square b0 square, right? So this will become half c e0 c square b0 square. So it looks like this is coming from electric part, and it's not very friendly. It's mixing electric and magnetic. So we know the C has both electric magnetic, so we'll write the C square a little differently. Half C epsilon naught 1 over epsilon naught mu naught. So in a way you can say, well, it looks very similar, so that I can write this guy 1 over C, I will C alone 1 over mu naught b0 square. Okay. Intensity does not give you direction, right? It just tells me how much energy is flowing past certain area per unit time. You would like to actually write something which is captures the intensity, right? You want to be able to say, hey, it's flowing in this direction and has this intensity. Well, that's where a pointing vector comes in. So if you look at instead of looking at S this way, if we define a vector called pointing vector, so as if, you can see here, as if I did this epsilon naught, okay, and just kept one of these guys, and the other one I wrote down C times B0, okay, and I just leave this alone, and then I wrote C as 1 over square root of mu naught epsilon naught. Then these two together will take me to square root of epsilon naught over mu naught. So if I multiply this guy with the square root of mu naught, so this will become a square root of mu naught epsilon naught over mu naught, and that, I'm just looking at the constants, okay, you can see it becomes 1 over C mu naught. Guess what? If I multiply this by C, I actually end up very similar to the intensity. So without actually going into the full thing, I'm going to do power crossing a surface can be, because I wrote down a vector now, I can use any orientation of surface and I can get dA. So you have to do this integral, and although this is interesting and quite powerful, I'm not going to pursue this further. What are the other things that's in the book that I didn't do? I didn't do kind of what's the momentum in electromagnetic wave. And another topic I would have liked to do is what's the radiation pressure. You might want to study on your own, but next topic I'm going to talk about is actually the topic of interference. Okay, so I'm going to stop here.